Okay, thanks for the organizer for the opportunity of being here. I need also to apologize because I'm going to talk about subbubbles. This has nothing to do with liquid crystals. But like Yair, I would be delighted to learn of unconnection of these things with the main topic of the conference. The title is Doughnut-shaped subbubbles, but there is a subtitle that in fact is the main message that I would like to convince you about. Is topological transition is mandatory in some isoperimetric problems. This is a work in progress. It started some years ago with a former student. This paper is available at the archive, of course. And the main outline of the talk, I will only remind some very basic facts about the classical isoperimetric problems, only to fix the language. Then I will introduce a kind of problem that I called over-constrained isoperimetric problem. Is in these over-constrained problems that the topological transition arise naturally. And I will finish taking a risk, daring to propose a conjecture. So we are talking about bubble. So the most important classical isoperimetric problem for our purpose is this one. The term, the closed surface of minimal area encloses a given volume V. Given volume V and fixed. This is something that can be described by variational calculus, very, very old stuff dating back from Euler, Lagrange, and these people. We are talking about real surface in R3, so this is two-dimensional manifold, so we can parameterize with two parameters, and the idea is to minimize the area functional with some extra constraint. In our case, the pertinent constraint is the constant volume. I will not enter in these details, but there is a standard strategy for this to introduce Lagrange multiply and things like that. But everyone knows the answer for this problem without any other constraint than the constant volume. And the answer is the sphere. Without any other constraint besides the constant volume, the smooth surface, a regular surface that encloses a given volume is the sphere. Of course, this is the case of the subbubble, because in the case of the subbubble, the only force that conforms this bubble is surface tension, and the energy associated with surface tension is the area. So to minimize the energy in the subbubble, it's equivalent to minimize the area. So subbubble are minimal area surface. Okay, this is the classical problem that I only remind to set up some notation. If the bubble has radius a, its volume is 4 pi a cubed over 3. Its equatorial perimeter is 2pa, and for our purpose here, it's much more interesting to describe the volume in terms of the equatorial perimeter. And we have this. It's L to the cube over 6 pi square. Okay, so this is our revision on the classical subbubble problem. So we can now start to talk some, I think, more interesting things. The first example of an over-constrained problem is this one. The term, the axisymmetric closed surface of minimal area enclosing a given volume V and with a fixed equatorial perimeter. The extra constraint, the pertinent extra constraint, is the fixed equatorial perimeter. Axisymmetry is not a pertinent constraint here. It's only because we can do the calculations analytically. But the new constraint that is pertinent is the fixed equatorial perimeter. Since we are working with axisymmetric surface, I will take advantage of this geometrical property. I will introduce cylindrical coordinates and consider this surface a surface of revolution. So this is standard material. So we have this the area functional to be minimized. This is the volume the constant of the constant volume, and the equatorial perimeter, it's only a point in cylindrical coordinates, so it's only to fix the point, that's the external point of the surface. With this simplification of axisymmetric surface, this reduced to a one-dimensional problem. It's a problem that we can solve easily. And the conclusion is, no surprise, that the surface has constant mean curvature. But these are surface of revolution with constant mean curvature. There is two types. The first is spheres and spherical caps and things like that. The second is piece of Delaunay surface. This is a classical surface that is very well known in classical geometry. Okay, so we can now try to ask this question. What is the closed surface, the axisymmetric closed surface, with minimal area enclosing a given volume and with a fixed equatorial perimeter? One case that's very easy to answer is this one. If the volume is related to the equatorial perimeter, but this relation, this is the sphere. The sphere is the minimal area surface for the free case. Of course, that will be also the minimal area surface for this case because the constraints are compatible. Only for sake of completeness, I will present a case here that's not our interest. Okay, this is the usual sphere. If you are lucky and have this relation between the volume and the equatorial perimeter. The next case is if the volume is bigger than the volume of the, I would say, equivalent sphere. The solution is something like that. You have a double structure. There is no, this inside part is not present. It's only because I took this from the internet. This is a double bubble, but exactly the same case. Okay, this is not a problem for us. The interesting things arise when we consider the reverse case. When we consider volumes that are smaller than the equivalent sphere. We can think if we have a volume that is smaller, but not smaller, is still close to the volume of a sphere with the same equatorial perimeter, we can think that maybe the solution could be something like a lens-shaped bubble. Okay, two spherical caps match together, one from inside, the other like this one, and you have a lens. And this is, in fact, the case if the volume is smaller than this, but not so smaller. If we take two spherical caps and we put one from upside, not for downside, we have a lens, and this is a good candidate to be a minimal area surface with a fixed equatorial perimeter. Yes, in the boundary is singular. No? The boundary, yes, yes. And in fact, this angle in the boundary is an important parameter that we will see. Okay, it's easy to see that this solution cannot be a good solution for small volumes. If you have a volume that's close to the volume of the equivalent sphere, it can be a good solution. But for a small volume, it will never be a good solution. And it's simple. If we calculate the volume of a lens, like this one, that you have radius A and height H, the volume is given by this simple formula. The area is given by this simple formula. And it's easy to see, if you take small h, you have arbitrary small v, but A tends to a constant. And the constant is twice the area of the discus. So this strategy of encase a volume with a spherical cap cannot be a good strategy for very small volumes. It turns out that in case small volumes, you need to use the other solution related to Doughnut surface, and it's this one. In this case, the external radius of the torus will define the perimeter, and you can enlarge the interior radius in the way that you have small volumes and small areas. What you didn't have in this case. In this case, if you take H small, you have a small volume, but H is not small. So this is a not good strategy to encase a given volume for axisymmetric surface. Okay. Yeah, no, the region inside is regular. Yes, the only singularity is on the boundary. Everywhere the surface has constant mean curvature. In particular, the mean curvature is well defined. Only on the boundary they have some problems. The section of the torus is this here. Okay, it's the inside. It depends on the parameter. The Doughnut surface has self-intersections. So the torus that appears here is the inside region of some proper appropriated Doughnut surface. I can show more details for those that interested in this thing. Okay. Why I'm talking about topological transition? Because I'm convinced that we have here an explicit example of a topological transition. I will do the following. I will start with a sphere with radius A, for example. We fix very interesting. This is an experiment that you can do at home. I will show you how to do with subbubbles. You start with a sphere, and you fix the equatorial perimeter. Then you start to deflate the sphere. You start to decrease its volume. So I will start with the perfect sphere, that's alpha equal 1, and then we are decreasing alpha from 1 to 0. And the result is this one. You start with a sphere, then the sphere is deflating. Oops. In some point, the minimal area is not anymore the sphere, but it will be the torus. And this happens when alpha is close to 0.21, that corresponded to a dihedral angle for the length of 60 degrees. Okay? So we have two situations that are topological different. For volumes that are in this range, the minimal area, the axisymmetric surface with minimal area encasing a given volume with a given equatorial perimeter is the length, I will call length bubble. And if for V is smaller than this, the surface will be a Doughnut bubble, a toroidal bubble. Okay, there is a lot of problems here with this. If we take this seriously as a model for subbubble, there is a lot of problems here. The first problem that we could check is to try to relax the axisymmetry. There are two ways of relaxing the axisymmetry. The first is to keep the axisymmetry in the definition of the problem. So I will consider minimal area surface with a given circumference as perimeter. And then I will allow to solutions that are not axisymmetric. So I will try to see if some kind of spontaneous symmetry breaking appears here. This is the first instance of relaxing axis symmetry I will consider here. This is a rather trick because it will depend on the details of the boundary. In particular, it will depend if the boundary is really a line or if it's a strip. This change completely the situation. But typically, the lengths are stable. The lengths are stable. The donut is unstable. And we can, it's not difficult to envisage some configuration that is not axisymmetric, that has an area smaller than this. You can think of something like this. You have a very thin torus, only to satisfy the constraint of the circumference, and then all the volume inside a sphere, for example. If you take this torus, as thin as you want, you have a very small area here. All the area will be in this sphere, and this sphere is the best way of enclosing anything. So there is a lot of, yes, sure. The problem is that if you take the torus arbitrarily is thin, then you're reducing the torus just in the region where the mean curvature is not defined. That is just in the boundary. Because the boundary is strange, because the boundary of the surface is not regular. So, yes. No. This is only. I'm not claiming that this is a minimal area configuration. I'm only saying that we can imagine something that could be a better way of encase some volume than this one. And the problem, the formulation of the problem is still axisymmetric. We are looking for a surface with a given circle as the perimeter. But now we are allowing to have maybe some non-symmetric solutions. Okay, the conjecture. The conjecture arises because we started to consider this problem. Not only we start to consider also surfaces that are not constrained to circumference. So you take n plane curve, and you look for a surface that has that curve as the equatorial perimeter, let's say, and then ask which of this surface you enclose a given volume with the minimal area. Of course, there is no hope of doing this thing analytically, so we use a lot this software that's quite well known in the community, the Surface Evolver, that's free and available at this address. It's very funny to play with this software. And we tested a lot of configurations, and it seems that the compilations of our results can be summarized in this that I call the conjecture, that oblate bubbles such that the volume is smaller than exactly that thing that we calculate for the axisymmetric case are always unstable. This would mean that a kind of pancake bubble should not appear among real bubbles. I don't know, real bubbles, for instance, in foams. It would be quite strange for me that in this situation you could have very, very oblate bubbles. So the conjecture is this one, that oblate bubbles such that with this relation, are always unstable and should not appear in real situations with bubble. Of course, practically, if you have a bubble like that and you deform the bubble break apart in the smallest bubbles. This is the idea. Huh? When I say that the bubble doesn't exist, it's because during the formation of the bubble will break apart in many smaller bubbles. I will stop here, and I need to say that I will be delighted to learn that this could have some relevance in some problem that you are working. Thank you.